You've seen one before. Maybe from a dock, maybe from a beach, maybe just in a photo someone posted. That wall of white steel rising out of the water, 20 stories tall, longer than 3 football fields, moving through the ocean like it has somewhere to be. And at some point, almost everyone asks the same question. Why doesn't that thing sink? Most people get an answer at some point in their life. Archimedes, displacement. The water pressure pushing up equals the weight pushing down. And that answer is correct. It is also almost completely useless for understanding what is actually happening on that ship. Because here is what nobody tells you. Flotation is the easy part. A beer can float. A plastic bag floats. A hollow chocolate egg floats. Flotation is not the engineering problem. The engineering problem, the one that nearly broke the entire cruise ship industry before it even got started, is stability. Staying upright, not tipping over. And when you look at what a cruise ship actually is, you start to realize that staying upright should be physically impossible. By the end of this video, you are going to understand exactly why. And the answer is going to change the way you look at every ship you ever see again. If that sounds like something you want more of, hit subscribe. We do this every week. Before we get into the physics of why these ships stay upright, let's settle the flotation question quickly, because it does matter. And most explanations get it slightly wrong in a way that makes everything harder to understand later. A cruise ship floats for the same reason a steel bathtub floats. Not because steel floats. Steel absolutely does not float, but because of what the shape of the steel creates. When you take a flat sheet of steel and drop it in water, it sinks immediately. The density of steel is about 8 times the density of water, so there is no contest. But when you fold that same sheet of steel into a hollow box, it floats. Why? Because now the steel is not just steel. It is steel plus air. And the combined density of steel plus a large volume of trapped air is lower than the density of water. Lower average density means it floats. That is the entire principle. A modern cruise ship is approximately 90% air by volume. The steel structure, the engines, the furniture, the people, the food, the fuel, all of it combined represents maybe 10% of the total volume of the ship. The rest is air. Cabins, corridors, atriums, restaurants, casino floors, theater stages, shopping promenades. All of that is essentially organized air trapped inside a steel shell. And that shell, despite weighing several 100 million pounds when fully loaded, displaces a volume of water that weighs even more. So, it floats. Archimedes figured this out in a bathtub in ancient Greece, and the principle has not changed in 23 centuries. The upward force water exerts on any submerged or floating object is equal to the weight of the water that object displaces. If you displace water that weighs more than you weigh, you float. A cruise ship pushes aside an enormous amount of water. That water weighs more than the ship. The ship floats. That part is genuinely straightforward. But here is what that explanation completely fails to address. A cruise ship does not just need to float, it needs to float upright. And those are two entirely different problems that require two entirely different solutions. Think about a wine bottle. Fill it with water and seal it. Drop it horizontally into a pool. It floats perfectly. Excellent buoyancy. Now try to float it vertically, standing up, cork pointing at the sky. Watch what happens. It tips over immediately. It does not sink. It just refuses to stay upright. The buoyancy is identical in both cases. The stability is completely different, because the physics of floating and the physics of staying right side up have almost nothing to do with each other. Now imagine that wine bottle is 300 meters long and 70 meters tall. Imagine it is carrying 6,000 passengers who are all moving around constantly, eating at different restaurants, standing on different decks, shifting their weight in ways that are completely unpredictable. And you are trying to keep that bottle not just upright, but stable enough that none of those people spills their coffee. In the middle of the North Atlantic, in January, with 50-knot winds. That is the actual engineering problem. And the reason it took the better part of the 20th century to solve it properly is that almost every feature that makes a cruise ship commercially attractive works directly against the physics of keeping it upright. I remember the first time this clicked for me with real clarity. I was standing on a pier in Barcelona, watching the harmony of the seas pull away from the dock. And I was watching the waterline, specifically how little of that ship was actually submerged. You look at a ship like that, and you expect it to sit deep in the water, like an iceberg, most of the mass hidden below the surface. But it does not. The hull drops maybe 8 or 9 meters below the waterline. Meanwhile, the superstructure rises 60 meters above it. 60 meters of hotel above the water, 9 meters of hull below it. I remember doing the rough ratio in my head and thinking, that center of gravity is sitting dangerously high. And then I started thinking about what would happen in a beam sea, with waves hitting that enormous broadside at regular intervals. And I realized the only reason that ship was not wobbling visibly was that something below the surface was working very hard to prevent it. The technical term for what I was thinking about is metacentric height. It is the measure naval architects use to quantify how stable a ship is when it tilts. If the metacentric height is large and positive, the ship strongly resists tilting and snaps back upright quickly when disturbed. If it is small, the ship is sluggish and wobbly but recovers. If it is negative, the ship flips over and stays there. Here is the problem with cruise ships. Everything that makes them commercially successful, the multiple decks, the tall superstructure, the amenities stacked high above the waterline, every single one of those features moves the center of gravity higher. And the higher your center of gravity relative to your center of buoyancy, the smaller your metacentric height, and the less inherently stable the ship becomes. Picture a bowling pin, wide at the bottom, narrow at the top. Now flip it upside down and try to balance it. That is roughly what cruise ship designers are asking physics to accept. Naval architects are essentially in a permanent argument with the product designers on every single ship ever built. The product designers want more decks, more amenities, more visual presence, more height. The naval architects are watching the metacentric height shrink with every floor they add, and trying to figure out how to compensate. A cargo ship, for comparison, is designed with stability as the primary constraint. The cargo goes low. The superstructure is minimal. The center of gravity stays close to the waterline. Cargo ships are passively stable in a way cruise ships simply cannot be. You could, theoretically, remove the crew from a cargo ship and it would continue floating upright indefinitely. Cruise ships are the exact opposite. They are, in the language of naval engineering, marginally stable platforms with active compensation systems, which is a technically precise way of saying they need constant help to stay right side up. This is where it gets genuinely strange. The first line of defense is the hull shape itself. The wide, flat bottom of a cruise ship hull is not just structural. It is a geometric stability tool. A wider hull means the ship has to tilt much further before things start becoming dangerous, because the cross-section of the ship at the waterline creates a restoring force when the ship tilts. Think of it like comparing a wide lamp base to a narrow one. The wider the base, the harder it is to tip. Naval architects maximize hull width within the constraints of ports, shipping channels, and Panama Canal locks. But hull geometry can only do so much. It helps with slow, gradual tilting. It does almost nothing for the kind of rapid rolling you get in heavy seas. For that problem, you need something active. And what naval engineers came up with is one of the most elegant solutions in the history of ship design. A system that lets the ship reprogram its own weight distribution while it is moving. A ballast tank is exactly what the name suggests. A tank, typically built into the double bottom and lower sides of the hull, that can be filled with seawater or pumped out as needed. A large cruise ship has dozens of these tanks distributed throughout the hull from bow to stern, and they can hold tens of thousands of tons of seawater in total. The critical engineering detail is not the capacity. It is the distribution. By pumping water from tanks on the port side to tanks on the starboard side, or from forward tanks to aft tanks, the ship can actively shift its own center of gravity in real time, without adding or removing any weight from the system. This matters enormously in practice, and in ways that most people never consider. A cruise ship does not load perfectly symmetrically. Passengers cluster. They all show up for breakfast on the same side of the ship to watch a port come into view. The fuel consumption across multiple engines is uneven. Provisions are loaded from one dock. Gray water accumulates asymmetrically. All of this shifts the center of gravity constantly, and in ways that cannot be predicted before departure. Without active ballast management, a large cruise ship would develop a permanent list within hours of leaving port, and that list would change throughout the voyage as fuel burned and passengers moved. The ballast management system on a modern cruise ship is adjusting continuously. You would never notice it as a passenger. There is no sensation, no sound, nothing visible. But below the waterline, thousands of tons of seawater are being shuffled through pipes from one side of the ship to the other, keeping the vessel level, keeping the center of gravity within the precise envelope the naval architects calculated. But here is what ballast tanks fundamentally cannot do. They cannot respond fast enough to waves. A wave can put a ship into a significant roll in a matter of seconds. Pumping thousands of tons of ballast takes minutes. So, for rapid, dynamic motion, the rolling and pitching that passengers actually feel during rough weather, something else is required. Something that can respond in fractions of a second with forces large enough to matter on a 200,000-ton ship. And this is the piece that most people never think about, and that almost no explanation of cruise ship physics ever addresses properly. Modern cruise ships carry active stabilizer fins. These are retractable metal foils, typically 2 to 4 meters in span, mounted on the sides of the hull below the waterline, roughly at midship. When extended, they look like small aircraft wings attached to the bottom of the hull. And they work on exactly the same principle as an aircraft wing, except instead of generating lift to climb, they generate hydrodynamic force to resist rolling. As the ship begins to roll to starboard, sensors detect the motion, and the stabilizer fins rotate to generate a lateral force that pushes back against the roll. The response time is measured in fractions of a second. The forces involved are substantial. Tens of thousands of pounds of lateral force, generated purely by water flowing over those fins at cruising speed, applied at a point on the hull that maximizes the restoring moment. The critical limitation that most people miss: stabilizer fins only work when the ship is moving. At low speed, or while anchored, water does not flow over them fast enough to generate meaningful force. This creates a real engineering problem, because cruise ships frequently need to operate at low speeds in port approaches, during embarkation, and while anchoring off tender ports. The moment you reduce speed significantly, you lose most of your stabilizer effectiveness. For exactly this reason, some of the largest cruise ships currently in service carry something that sounds considerably more like science fiction than marine engineering: active gyroscopic stabilizers. These are massive spinning masses, sometimes exceeding 20 tons, mounted on precision gimbals inside the hull, typically low in the ship, to keep the center of gravity favorable. When the ship begins to roll, the gyroscope resists the change in orientation through angular momentum. The mounting system is actively controlled to direct that resistance precisely where it is needed. The result is that a 20-ton spinning mass, working through fundamental laws of rotational physics, can produce a measurable and significant dampening effect on the roll of a ship displacing 200,000 tons. The first time I worked through the technical specifications on a large ship gyrostabilizer system, I spent an embarrassing amount of time checking the math. Not because I doubted the physics. The physics of gyroscopic precession is not in dispute. But the ratio is so extreme that it takes a moment to accept. A 20-ton flywheel doing useful work on a 200,000-ton ship. It works because gyroscopic resistance scales with rotational speed squared, and these systems spin at several hundred revolutions per minute continuously. The physics is unambiguous. The engineering to make it practical took decades. Above all of these physical systems sits the control layer, the ship's integrated stability management system. And this is where modern cruise ship engineering stops feeling like naval architecture and starts feeling like aerospace. This is software running on hardened computers with redundant power supplies, monitoring dozens of sensors simultaneously and continuously. Inclinometers measuring tilt angle in real time. Accelerometers measuring roll rate and acceleration. GPS tracking exact position, heading, and speed. Weather sensors feeding wind speed and direction into stability calculations. Draft sensors at the bow and stern measuring how the ship is sitting in the water. All of this data feeds into algorithms that are calculating thousands of times per second whether the ship is within its stability envelope and what corrective action is needed. The system does not sleep. Between sensor readings, between adjustments, there is no pause. The ballast pumps receive commands. The stabilizer fins receive angle corrections. If conditions deteriorate beyond software thresholds, the bridge crew receives alerts. If conditions deteriorate further, the system escalates. Every sea state, every loading condition, every weather event is being continuously assessed and responded to. Here is the detail that I think puts the whole picture in genuine perspective, and that I have almost never seen mentioned in any popular explanation of how cruise ships work. The stability margins on a cruise ship are deliberately kept thin. A naval architect designing a cargo vessel will build in enormous passive stability margins. The ship will be so inherently stable that active systems are essentially backup redundancy. But a cruise ship cannot do that. Every unit of inherent passive stability you build into the design through hull geometry and ballast positioning costs you something, usually draft, which limits what ports you can enter, or beam, which limits the shipping lanes you can use, or internal volume, which directly limits how many revenue-generating passenger spaces you can fit. The more passively stable you make a cruise ship, the less commercially viable it becomes. So cruise ships are deliberately designed to sit near the lower boundary of acceptable stability under normal operating conditions, and then surrounded by multiple overlapping layers of active compensation that keep them safely within that boundary at all times. It is not a design flaw. It is not an oversight. It is a calculated engineering decision made with full awareness of what it requires. The alternative is a ship that is inherently stable, but cannot generate enough revenue to justify its construction cost. What this means practically is that a modern cruise ship is always operating closer to the edge than it appears from the outside. The stabilizer fins are not a convenience feature. They are a primary stability system. The ballast management is not optional trim adjustment. It is structural to how the ship operates. The stability software is not a safety net added by regulators. It is a fundamental reason why the ship can exist in the form it takes. Remove those systems, and the physics asserts itself. Quickly, there have been incidents over the years. Not disasters. Modern redundancy design is genuinely excellent. But incidents where partial system failures or extreme sea states pushed ships into unexpected roles. Unsecured furniture moving across dining rooms, passengers losing their footing on open decks, pool water sloshing over the sides. These events are rare, and in well-maintained modern ships, they tend to be minor. But they are useful reminders of what is always present just below the surface of normal operation. The permanent tension between a structure that wants to be a skyscraper and an ocean that has no interest in accommodating it. So the next time you are standing at a gangway, about to board one of these ships, looking up at 20 floors of balconies and sun decks and restaurants and theaters, here is what you are actually looking at. You are looking at a structure that floats because it is 90% air wrapped in steel, and because Archimedes described the relevant physics accurately in 300 BC. You are looking at a platform that is, on its own, not inherently stable enough to cross any serious ocean safely. You are looking at the result of a century of naval engineering that solved that problem, not by making the ship passively stable, which commerce would not allow, but by building systems intelligent enough to compensate for the instability continuously, in every sea state, across every loading condition, for the entire operational life of the vessel. The flotation is the easy part. Any hollow steel box can float. The stability is the problem that took a century to solve. And the solution is not passive, not structural, not a property of the ship itself. It is a behavior, a constant, automated, never-sleeping act of engineering maintenance, happening every second the ship is in the water. Archimedes got the first half right in his bathtub. It took the rest of engineering history to figure out the second half. That is the real reason it does not sink. If this changed how you see these ships, subscribe. New video on screen right now, and I think you are going to want to watch it.